Alright, we're going to be looking at position, velocity, and acceleration. So we're going to actually start doing something with this derivative stuff that we've been learning. And I remember when I first started studying this particular part of calculus, it was pretty exciting. But unfortunately, we are going to be looking at projectiles more or less that are going traveling in a vertical manner, going straight up and coming straight back down again. So there's no angle of elevation involved, and that's later on in calculus we'll be dealing with that. But and one other thing here, we've really simplified the problem down, and we're neglecting air resistance and some other factors that are involved in projectiles. But so we just want to simplify some things down and just kind of focus on the simple stuff first, and then gradually get difficult. Okay, so we got to get started here. This I really cover a lot in this problem. What we've got here is we've got a ball, and it's dropped from a height of 200 feet. Its height is s at time t in seconds, and is given by the position function. Okay, so this tells us how high the ball is from the ground at some value t. Now I'm using these English units here, feet, and some of the other problems will be using meters and seconds, meters, but we'll start off with feet here. So the first question we've got here, or it's not really a question I guess, but we want to find the average velocity over the time interval 1 to 2. And then we're going to find the instantaneous velocity when t is equal to 1 and t is equal to 2. And then we're going to find the acceleration when t is equal to 1 and t is equal to 2. So we're just going to be looking at this interval here, even though I do have a chart drawn out with some other stuff. So let's get busy. Let's find the average velocity. Now this is going to be the same thing as finding the average rate of change over the interval that's in some previous problems. Okay, so here's our position function right here. Now remember, to find the average rate of change, we used this, and we were on some interval. Well, here's our interval. We're between 1 and 2, and so we just do s of 2 minus s of 1 over 2 minus 1, and that gives us our average velocity. So when we plug 2 into our function, as I've got stated here, and then minus, then plugging 1 in to the position function, and then taking their difference, and of course 2 minus 1 is 1, we get negative 48 feet per second. So that's going to be the average velocity between 1 second and 2 seconds. Well, let's say we wanted to find the instantaneous velocity at 1 second. Well, we would take the position function here, then take its derivative. So the derivative of negative 16t squared is negative 32. And then we just plug 1 in, and that gives us our instantaneous velocity, which is going to be just negative 32 feet per second. Which I guess I've got stated here. And then we wanted to plug 2 in, and so this gives us negative, it looks like 64 feet. So plugging 1 in, we get negative 32 feet per second, and plugging 2 seconds in, after 2 seconds, it's now traveling at negative 64 feet per second. So as you can see, that average is falling in between negative 32 here and negative 64. Okay, back up to the problem. So this was part 2 here on instantaneous. What about the acceleration at 1 and 2? Okay, well, to find acceleration, first we take the first derivative. Now the first derivative gives us the velocity, which we usually say v of t. And the second derivative is going to give us our acceleration, which we denote as a sub t. And that's equal to negative 32. So no matter what we plug in for t right here, it's still going to remain constant, negative 32 feet per second. So as you can see, acceleration is constant for any value of t within our domain. Now I wanted to come up here and take a look at this picture here. So I've got our graph drawn, and this represents the position function. And then this is at 1 second, and this is at 2 seconds. And you can see this is just the slope of a tangent line here, or just the segment, and then the slope of another tangent line right here. Okay, so we've got the slope at 1 and the slope at 2, and we said that the average, remember, was somewhere in between here. And remember, to find the average, what we were doing is we were taking really, if we drew a line through this point here, and then drew a line through this point here, or I should say we drew a line through that passed through both these points right here, what we're finding is the slope of the secant line, and that happens to be our average velocity between 1 and 2. Now what I'm going to do next here is I'm going to show you a chart, and we're going to kind of look at the average velocities between 0 and 1, and then 1 and 2, and then 2 and 3, and so forth, and kind of look at these average velocities and maybe see a pattern or something. But this graph over here is the graph of the velocity function. So as you can see here at time 0, right, it's 0, but then as you notice that the graph is below the x-axis, right, the graph is below the x-axis, and because the velocities are all negative, right, the velocities are all negative, and that kind of tells us that this thing is falling, okay, that tells us that it is falling when it is negative. But let's look at that chart I was talking about. Okay, first off, don't worry about what's going on here. All right, we've got some time intervals, which is obviously in seconds, and we're looking at they're in increments of 1 second here. And this ds right here is the difference. I'm saying ds is the difference in feet. The difference in feet. So the difference in feet between 0 and 1 second. The ball traveled, or whatever it was, I guess I'm looking at this as the ball, anyhow, traveled 16 feet. Now this is the difference here in velocity. Now the difference in velocity is the acceleration. The difference in feet is the velocity. The difference in velocity is the acceleration. Okay, I hope I got that straight. But anyway, so we're looking at averages here, and then so what can we see here? Well, we can see that as the object is falling, its velocity is increasing, right? Its velocity is increasing. And of course, what's happening here, the acceleration, or the difference in velocity, or the acceleration is staying constant, right? Acceleration is staying constant. So let's look at this picture I've got drawn. Okay, so this right here is the actual curve, okay, of the graph of the position function. So as you can see right here, let's see, this is 2, 3, right, 4, and this looks like 3.5 or something like that. This is where the object is actually now on the ground, right here at 3.5, right? The distance between the object and the ground is 0. Now what this is showing here is it's dropped at 200 feet, and then after 1 second you can kind of see the distance here, and remember that was a difference of 16 feet, and then between 1 and 2 seconds it has look what's happening here. Right, so this is just increments of 1 second here, differences of 1 second, right? First, after from 0 to 1, and then from 1 to 2, and then from 2 to 3 seconds. So you can see here, look at here, this distance here is increasing, right? And it's not, yeah, look how it's increasing right here. So that's quite interesting. At least I think it is anyway. Okay, got one more chart here. We've got, this is the interval between 1 and 2, and this is the first derivative, right? The velocity, giving us the velocity, and as you can see here, I just it's increasing by 0.1, and what's happening? You can kind of see what's going on here. Now, the whole idea was to take the average, and I've added all these up, divided by I can't remember, 11 or something, and had to go back and make a correction here, and that is this shouldn't be v prime here. Okay, that would be the derivative of the velocity function, which would give you the acceleration function. So this is just a v, and then I'm testing out at 1 second, and then 1.1 seconds, and so forth. And so we were just kind of analyzing and looking at what's happening in the interval between 1 and 2. And as you can see here, I go through at increments of 1 and find the velocity at 1 second, then 1.1 seconds, and then so forth. As you can see, these numbers are more or less increasing. And of course, the negative, remember, tells me that this ball is actually falling. Now, the whole idea here of this is to, let me scroll down the screen. I was curious to know what is the average instantaneous rates at each one of these points here, 1 and 1.1, 1.2. So what I have done is I found the velocities you can see here at each one of these increments, and then added them all up and divided by 11, because there's 11 data points here. And we end up with something quite interesting. We end up with the average of this data here is negative 48 feet per second. Not per second squared. I don't... Hold on. Okay. Anyway, we end up with an average of negative 48 feet per second. And if you can remember that this was the average velocity, or the average rate of change between 1 and 2, which happens to be also negative 48. So is that just a coincidence? Well, I don't know. I guess I'll let you determine that. Is that a coincidence that the average rate of change, and then I just took a whole bunch of them here together, divided by 11, and end up getting that same number? So I don't know, coincidence or not. Let's. I just want to look at the graph here one more time. Okay, so here's the graph, and I wish this was zoomed in a little bit more, but it's not. And so 1 second is right here on the t-axis, I guess you could say. And so the slope of the line, so that was our first one in that data table. And then at 2 seconds, this is what the slope was at 2 seconds. And what I did was I went in increments of 0.1, so it was 1.1, and if you can imagine, we draw out another tangent line right here, and then at 1.2, right, we find the instantaneous rate, right, because these are instantaneous rates here. And then we added all of these slopes up between 1 and 2. We added them all up and then divided by, there was 11 of them, and we got negative 48. And it turns out that that also happens to be the same as if I just took a line and passed it through this point here and this point here, and then found the slope of that line, which also happens to be negative 48. Is that coincidence or not? Well, you determine. Right, so remember, to find the average rate of change, or our average velocity, this is what we did. Right, just to refresh your memory, I know it was a long time ago, but we ended up with a negative 48. Let me scroll down the screen here a little bit. All right, and as you can see, the average velocity is negative 48 feet per second, and that happened to be the same number as if we summed up all the instantaneous velocities at increments of 0.1 from 1 to 2. All right.